Hey everyone, so today we're going to be doing question 4.1 from Elements of Programming Interviews in Python. The question is called Compute Parity, and we want to return the parity of a 64-bit integer. So return 1 if there's an odd number of bits set, and 0 if there's an even number of bits set. So for example, if we're given the number 14, we want to return 1 because 14 expressed as binary would be 1110. That's 3 ones, we return a 1. If we're given the number 6, 6 expressed in binary is 110, so we return 0. And the operation that we're going to be using to compute this is called the XOR bitwise operation. There's going to be a link in the description to learn more about XOR, but for the purpose of this video, all we need to know is that 0 XOR 0 gives us 0, 0 XOR 1 gives us 1, 1 XOR 0 gives us 1, and 1 XOR 1 gives us 0. So it's an exclusive OR operation, meaning either the first bit is set or the second bit is set, but not both. So if both bits are set, we give 0. If just one of them is set, we give 1. If neither are set, it's also 0. So a quick brute force algorithm for this would just be to iterate over the bits of the integer and count if there's an odd number or an even number of bits set. So the way we would do this is we would have a parity variable that we would initialize to 0, and then we would go bit by bit. And the time complexity for this would be O of number of bits in X. So we're going to terminate after we have no more bits to calculate. So we'll say while X, parity is going to be XORed with whether or not X has the first bit set. So here X and 1 is going to check is the first bit set. So X and 1 gives us an answer to is the first bit set. And then we will XOR this. So at the end of our iterations, if we've done an odd number of XORs, we will be ending up with parity equals 1. If we did an even number, then we're going to end up with 0. Then in order to move on to the next bit, we're simply going to shift X over to the right by 1 bit. And then we simply return parity once we break out of this while loop, which will happen once X is 0. So let's test out our solution real quick. And we quickly pass all of our 10,000 cases in 8 microseconds. So now let's take a look at some ways that we can improve this. So for example, here we're checking the parity each time we have a bit. So if we have something like 1 with a bunch of zeros and then a couple of 1s here, we're going to be checking through this loop for every single 0. And even though this is going to work, I mean, we can see that each time we're going to shift X over by 1, so we'll be, we'll check this value, we'll see that there's a 0 here, we're not going to update parity, we're going to shift it over again, shift it over again, we'll see that there's a 1 here, we're going to flip our parity bit to 1, we're going to shift it, we'll flip our parity bit again back to 0, then we'll keep going, we're going to be doing all these iterations, and then at the end counting another 1. So of course, if we know we have 64 bits, then the solution is still going to be O of 1, but it's going to be O of number of bits in X. So if we didn't have a 64-bit integer, it would be much slower. And that leads us to our second solution, which would be check the last set bit. So another interesting bitwise operation is x and x minus 1. So this is a little trick that can be used to remove the last set bit. And we can see this by looking at, some examples. For instance, 1, 0, 0. So if we were to subtract 1, we would end up with 0, 0, 0, 1, 0, 0, 0. And now if we were to subtract 1, we would take this 100, 1, 0, 0, and it would become 0, 1, 1. So if we were to look at this and we were to AND this, we would get 0b 0, 0, 0, 1, because both of the ones are set. Then we would get 0, 0, 0, 0, 0, 0, 0, because 0, 1, 0, 1, and 1, 0 all AND to 0, because it's not both of them being set. So you can see here that by doing x minus 1 and x, we've removed this one bit. So if you compare these numbers side by side, we see that we've removed the rightmost set bit. So instead of saying last, we can say rightmost set bit. So how do we take advantage of this? We can say while x, we'll say parity XOR equals 1. That means we've hit the loop once. And because we know x is non-zero, we know that there's at least one set bit in x. So we'll say flip to parity. And then we'll say x and equals x minus 1. So we're saying here, remove the last set bit. Here we're saying flip the parity. So after we've exited this loop, we can return x. And let's test out our solution. Let's take a look at what's wrong. Oh. Here we're returning parity, of course, instead of x. And again, we've passed all our test cases, except this time you can notice that it's in 3 microseconds rather than 8. And the time complexity here, of course, is going to be O of number of bits set. So this is a substantial improvement because we're always going to have less set bits than we are number of bits in x, because, well, the only time it's going to overlap is if we have something like 1, 1, 1, 1, 1, 1, 1, dot, dot, dot. In which case we're going to have the same number of iterations. But otherwise, if we have a sparse number in binary, something like 1 and a bunch of zeros, and then a 1, then a bunch more zeros, maybe another 1, then in this case, in our second solution, we're only going to be doing 4 iterations. So each time we hit a 1, we remove it, and then we flip our parity. So here we're going to remove it, set this to 0. Parity is going to be flipped to 1. We're going to move on to this bit. We're going to flip our parity, which is going to set it back to 0. We're going to move on to this bit. We're going to flip our parity back to 1. This bit gets flipped to 0. We're going to flip our parity again back to 0. We're going to flip this bit, and x is now going to be all zeros. We're going to exit our loop, and we're going to return 0, which makes sense because we had an even number of 1s in our binary number. So let's see if we can get an even better solution. So one thing we can look at is we can exploit the fact that we know we have 64 bits. So for instance, let's take a smaller example. Let's say we had 8 bits. So let's say we had 0, 0, 1, 1, 1, 0, 1, 0. Then we can think of this next approach as folding the binary number in half. So if we were to split it in half and put it side by side, and we were to compare 0 and 1, 0 and 0, 1 and 1, 1 and 0, we would end up with a 1 here, a 0 here, a 0 here, and a 1 here. So now let's forget about these two numbers. Let's do the same thing here. Let's split it in half and then compare these two numbers side by side. Well, 1 and 0 is going to give us a 1. 0 and 1 is also going to give us a 1. Then again, we split it in half and we compare the two numbers. 1 and 1 is going to give us 0. So our final parity is going to be 0. And if we were to look at our original number, we do in fact have 1, 2, 3, 4 ones, which is an even number, so we do want to return 0 as our parity. So implemented for a 64-bit number, this would look something like this. X XOR equals X shifted over by 32. So this is us flipping it in half once, and then storing the result of the XOR operation back into X. So now the only values we care in X are in the first 32 bits. So if we do this again, we'll say X XOR equals X shifted over by 16. We can do this again, shifted over by 8. Again, shifted over by 4. Again, shifted over by 2. Again, shifted over by 1. And then what do we return? Now we have to return X, but not the entire integer X, because in the leftmost bits, there might be some leftover stuff from this initial, all of these operations. So all we really care about is the rightmost bit now. And if it's set, we know that that's our parity. If it's not, then we know that the parity is 0. So if we run this again, we pass all our tests, and this time we pass them in 1 microsecond. Because for a 64-bit integer, we're guaranteed to get the answer in just 6 bitwise operations, well 7 if you include this return. So this is going to be O of log n, where n is the number of bits. And this is a little bit hard-coded for 64, but you could just as easily put this into a loop if you were to be dealing with the parity of a very high number of integers. So here, this is 3 highly efficient ways of calculating the parity. But what if you had a follow-up question that, let's say we were using this function all the time. Let's say we knew we were constantly having some highly compute-intensive process calling this parity function, and we needed to squeeze out every bit of performance. So one thing that we could do is we could use a lookup table. And we could use this parity function to populate this lookup table, and then instead just return the values from the lookup. So if we call this, for instance, populate parity, and then below we were to have a lookup table, just a lookup dictionary, we can call our def, we can populate it by saying for I in range 164. This is a shorthand way of saying the largest 64-bit integer. We would say lookup I equals populate parity of I. And then in our parity function, we would simply return lookup of x. So one thing to note is that 2 to the power of 64 is quite a big number. And if we were to run this, it would actually take quite a while just to populate this lookup table. So a trade-off that we can do here is, well, we can populate the first 16 bits. And then if we know the 16 bits, then each 64 bits we can express as A, B, C, D, where each one of these is, A is the first 16 bits, B is second, C third, D fourth. And then if we could just return A XOR B XOR C XOR D, then we have parity with X. So how can we do this? We can do this with the help of what's called a bit mask. So let's say this mask is going to be just all ones in the first 16 bits. So we can express that as OX FFF, and this is the hexadecimal representation for F is the hexadecimal representation for 16. So we have essentially 4 ones here, 4 ones here, 4 ones here, 4 ones here. So it's OB of 111, 111, 111, 111. And then when we return, instead of just lookup X, we're going to return the first 16 bits, which is going to be X shifted over by 48. And then we're going to XOR that with lookup of the second 16 bits. So that's going to be X shifted over by 32. And then ANDed by the mask. So we're going to look at, when you think of the mask, think of it as, for a small example, let's say our mask was 0, 1, 1. Let's say it was just 0, 1, 1, and we had this long integer, or binary integer. If we were to AND it with the mask here, we would be left with 1, 0. If we were to shift this number over, so we were to say, and then we were to AND it with the mask, then we would get the second 2 bits. So this would be 1, 1. Then let's say we shifted it over another 2 bits. We would AND these two, get 1, 1. Let's say we shift it over again. So we can keep going, and using this we can extract the last particular number of bits. So we're using this X shifted over by 32 to shift X by 32 bits, and then we're using the mask to cut off the first 16 bits, which might be extra. Then we can do the same thing and say lookup X shifted over by 16. And then we can say lookup of X with the mask. And now if we were to call parity, we would get all of our tests passed in 2 microseconds. And it's slightly slower than our original solution simply because it does take a little bit of overhead to populate this parity array, the lookup table. However, keep note that our follow-up question was, what if we had to call this parity function not, 10,000 times? What if we had to call it, say, 1,000,000 times? Well, in that case, doing only 4 or only 3 XOR operations and then a few binary operations is going to be marginally better than our solution here, which used 6 shifts over here and 6 XORs over here and then an AND here. So if you look at the total number of binary operations, here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then in this solution, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are 3 very good solutions for the parity problem. And this is also a technique with the lookup table that you can use for many questions. But it's in particular useful here just because of these binary bitwise operations that we can do. And the tool that we use to verify our solution is the EPI judge in Python, for which there will be a link in the description. And if you'd like to learn more, check out the link. You can find mentoring and resume reviews. Otherwise, see you in the next video.